All right, the topic I'll be presenting today on is controlled release of pesticides from biodegradable polymers. Um, this is a topic I personally find interesting. I was just researching papers on biodegradable polymers, and this idea happened to pop up. It's an idea that I had also brought up recently at where I work, where we compound custom polymers, and this was just one of the ideas that we had happened to be discussing about pursuing, and I found it interesting that I had come across this paper. So this is what I chose to present. And this is the structure we'll be following for the presentation, basically a brief introduction and background on the agricultural business, current problems that they're facing, and then from there, the controlled release of pesticides in agriculture, the preparation of formulations for controlled release from biodegradable polymers, encapsulation in a biopolymer matrix, and then the manufacture of those microcapsules, and environmental considerations, and then finally discussion on the paper and conclusions about the paper. So, quick background on agriculture and some of the criticisms. Several of the criticisms include soil erosion, salination, draining of aquifers for irrigation, and chemical pollution, mostly from pesticides, but also some other sources, just like animal waste, crop waste. Um, Synthetic chemicals and pesticides are used to improve crop yields. Otherwise, just we lose the efficiency without these chemicals. But these chemicals leave behind toxic remnants that will persist in the environment. A couple of classes of these chemicals are carbamates and organophosphates. Um, just think of like Roundup, glycophosphates. Not necessarily the healthiest chemicals to be around. They're great for keeping crops growing, but major carcinogens in humans. Um, yeah, and just basically there's a need for environmentally friendly pesticides to reduce levels of toxins in the environment. And some of those options include biodegradable molecules that won't persist in the environment. Other methods to reduce this do include the controlled release that we were talking about. Um, Basically, I'll talk about it on the next slide actually. So using controlled release in agriculture. So a kind of startling fact is that only about 0.1% of pesticides used reach the target pest. The rest will accumulate in the soil, run off into groundwater, and that's a major issue. Just getting away from the fact of waste from like a monetary standpoint, this is devastating to local environments and local ecosystems. Controlled release is a way to reduce this issue. Um, as seen on the graph on the side here, you can treat a field once and pesticide concentrations will stay above a effective threshold for much longer than conventional release of just spraying crops with pesticides, where you get a quick peak and then it quickly goes below effective levels, meaning that you'll have to treat fields several times over the course of a growing season, which will also lead to more waste and more runoff, as opposed to the controlled release methods. All right, the figure on the right has several different methods of preparations used for controlled release systems. Your first one is a polymer active ingredient conjugate system, and this is basically where you have a drug or pesticide in this case covalently bonded into your polymer. The second method here is matrix-based systems. This is basically where you have a dispersion of your active ingredient inside of a polymer matrix. This is something that's commonly used in time-release drugs as well in agriculture now, well, where they're attempting with agriculture. And basically, as the polymer degrades, it releases more and more of the active ingredient held inside the matrix. The third system here is a membrane-based system, similar to the matrix-based system, except for all of your active ingredient is kind of held together in a pool inside of a membrane, and as the membrane dissolves, it will release all the active ingredient. And this is another method that's commonly used for drugs, basically to survive your stomach conditions and only release drugs after, because some drugs are sensitive to the acid in the stomach. But this is also a method they're considering in agriculture. The method D there is a hydrophilic matrix system. This is like a hydrogel, pretty much, also used in drugs, drug delivery. Basically, as the material gets wet, it'll swell, allowing the active ingredient to escape the matrix. And finally, we have a stimuli responsive system, and these systems are very targeted. They're used for targeting pests directly. Basically, the conformation of the matrix will change as it comes into contact with certain stimuli, maybe heat, moisture, or in agriculture's case, specifically the roots of the target pests. And when they come in contact with that, they'll release the pesticides, making a very controlled release. Now, for release of the active ingredient from biodegradable polymers to happen, there needs to be degradation of the polymer. Now, in the bulk state, typically, the polymer chains are too large for organisms like bacteria, fungi, algae to break them down. So the first steps that need to happen are some sort of bulk degradation. And this typically comes in the form of UV or hydrolysis. The major one is hydrolysis. Many of these biopolymers are susceptible to hydrolysis. So basically this will break down the polymer until it is in small enough segments for microbial organisms to take over. And then, once it gets to this step, it's basically enzymes from fungi and bacteria and algae that will continue the degradation. So besides just being able to time your release, encapsulation in a biopolymer matrix has other benefits as well. It prevents volatile ingredients from evaporating. This is an issue with pesticides, which are typically semi-volatile. It also converts difficult to handle liquids, and also unsafe to handle liquids, into easier to handle powders. And when the active ingredient is encapsulated in the polymer to create a powder, it's also less hazardous to anybody who would be handling it. So the figure on the right shows some of the polymer types that are used as the biopolymer matrices. Chitosan, pectin, lignite, they're all fairly naturally occurring molecules. And in order to make the encapsulation matrix, these are typically compounded together with the active ingredient. And just a quick overview of microcapsule manufacture methods. I won't go too deep into any of these because we'll be running out of time. You have physical and chemical coating. For physical coating, you have pan coating, fluidized bed, and spray drying. And then for chemical coating, you have interfacial polycondensation, interfacial cross-linking, and in situ polymerization, which is one of the more interesting ones. So for environmental considerations, direct application poses the greatest environmental risk. As mentioned before, only 0.1% of your pesticide is reaching into the target pest. That means you have 99.9% running off into drinking water or just contaminating the soil, making it unusable in the future once the pesticides accumulate to a certain amount. Also, polymer degradation products must be considered. Just because they are biopolymers doesn't automatically make them safe for the environment. If you had a buildup of all these polysaccharides in the soil once they're degrading, there could be issues there that should be looked into. But that being said, bio-based or carbohydrate-based polymers typically have safer degradation molecules than, say, if you're degrading PET or polyethylene. But like I said, it should be studied and shouldn't just be assumed. And then crosslinkers and other additives used in the polymer matrix should also be considered for their environmental effects and accumulation effects. So for my thoughts and just a bit of discussion on the paper. First off, what they didn't consider was controlled release using petro-based polymers, such as polyethylene PET. I know in the last slide I said that these are typically less safe for the environment, but there currently are new additives being added into the market which allow for these to be broken down by microorganisms in similar ways that the bio-based polymers would be broken down in, making them more useful for these kind of applications. One of the biggest barriers to entry into agriculture would be the cost of using a controlled release system. And if you're able to use something like polyethylene or PET, a more consumer grade polymer, that would drop the cost dramatically, making this much more likely to be used by farmers if it's something that's able to be done in a safe way. And like we had mentioned on the last slide, natural doesn't necessarily mean safe. If any of these biopolymers have some sort of hazardous metabolic path that they go down when being degraded by microorganisms, or just are persistent molecules, that doesn't necessarily make them better than the petrol-based polymers for this kind of application. At the same time, too, microplastics are still a problem here. Just because they're bio-based doesn't mean they aren't microplastics. And if they end up in a environment where they're not going to degrade, they have the same issues that microplastics currently face. And finally, another idea that the paper had discussed was making this controlled release system possible to be used with irrigation, just so basically like a farmer would have a one-size-fits-all mix of water, pesticides, nutrients, and just the issue there would be once you're starting to create a water-soluble product, you would still run into those runoff issues of pesticides, leading to potential accumulation in the environment, which should be considered and avoided. At the same time, is if you are adding this product into water, or these types of biomolecules into water, basically the main degradation pathway that we discussed was hydrolysis. So you're going to see that these polymers may leach out whatever active ingredient is held inside if they are contained in a pool of water, which again would lead to runoff and other issues, unintended issues. So that would just need to be considered. And just some brief conclusions. Just this type of research is always a step in the right direction. Anytime we're trying to reduce waste and the environmental impact, it's just always a good field of study. Again, just harping back on the point where 0.1% of pesticides is actually useful in their end goal. Something like controlled release could cut back use of pesticides by 1,000 times, which would be great from a cost perspective for farmers and an environmental perspective for everybody else. And yeah, just reducing the environmental impact is imperative for being able to continue life as we know it on this planet.